Hi everyone. I want to walk you through the answers to this free fall think sheet because some of these questions are just confusing. They're confusing in the way they're written. They're also confusing because they give you a lot of information. You've got to be able to pick out the important pieces and also visualize what it's actually saying. That's going to help you with a lot of physics problems, trying to visualize in your mind what's happening to this object in motion. So we're going to walk through these answers. I'm going to go a little bit fast because you have the answer key available to you in the classroom. Some of these I've written the answers to, some of them I haven't. So we're just going to walk through them. I'm going to explain why we're seeing what we're seeing in the answers. And then you can, of course, check the answer key in the classroom when you're ready. So first, figuring out the speeds for each of the speedometers. To figure out the speed, we can use this equation. I got this equation from our average acceleration equation, which has velocity over time. We already know the average acceleration for any falling object is negative 9.81 meters per second squared. Now, sometimes they use the negative, sometimes they don't. For most of this worksheet, they've used 9.81 meters per second as a positive value. So if that helps you get the right answers or helps you match them up better, use the positive, but know that you're not wrong in writing it as negative either, because that acceleration is in the downward direction. So we know that acceleration due to gravity is 9.81 meters per second squared. We're also given our times for each of the speedometers. If we want to figure out just velocity, just speed, we can multiply by t on each side, meaning that our velocity at any given time can be solved by taking 9.81 meters per second squared times time. That's how I filled in all of those arrows. I noticed that at every second we fell, our velocity increased by about 10 meters per second, which lines up with what this constant value of gravity's acceleration is. Now, once we figured out those speeds, we also are asked to figure out the meters this rock has fallen, its displacement from 0. That's important. Because this rock is starting from rest, and we have to use the equation that includes gravity or acceleration, time, and displacement, we can get rid of a couple variables because it would be 0. Yi is 0 because its displacement is 0 to start. Vi is 0 because its speed is 0 as long as it's not moving. So that simplifies this equation to the following. 1/2 times accelerations due to gravity times the time we're asked squared will give us this value for every second we're solving for. Now, question 2 asked, where's acceleration the greatest? It's kind of a trick question because as long as we're ignoring air resistance, our acceleration is the same throughout the entire fall of this rock. It's always 9.81 meters per second squared in the downward direction. At which of these times is our speed the greatest? Speed's not always constant. We can see that because the speedometer is always increasing by 10 meters per second. If it's always increasing by 10 meters per second, that means our max time is our max speed, 5 seconds. Number 4, we're asked to compare some of these variables to figure out what kind of relationship does time and distance have for a falling object. Well, I saw that as we moved from 2 seconds to 4 seconds, so time doubled, our distance increased by a factor of 4. So as our time is doubled, our distance always increases by a factor of 4, so 20 times 4. That fills in our blank here. Backside, we're analyzing Missy DeWater's dive from the platform. First, it asks you to tell us what is her acceleration. And since she's a free-falling object, her acceleration is 9.81 meters per second squared. However, when we're making that statement, we're assuming that air resistance is not affecting her. Now, we're asked to represent her velocity with arrows. Her velocity is increasing as her time falling increases, so I try to increase that arrow by roughly the same amount for each position of her fall. That's how I drew in those arrows. Now we fill in the table. To figure out velocity, we use the equation g times t. You're given the time here. To figure out distance, we use the second equation we used, half times 9.81 times the time squared. And then to figure out the height for each of these placements, they have a couple extra here with the times. You have to take your initial height minus how far you've fallen. So 19.6 minus 1.2 gives you 18.4. 19.6 minus 4.9 gives you 14.7, and so on. Now this last problem is a little tricky if you're not a sports person like me. I was asking myself, what does hang time mean? Hang time means how long Michael Jordan is in the air as he's jumping and landing. So Michael Jordan has a hang time of 3 seconds. We're going to use our equations to figure out the height at which he could leap. So what's his max height? If he's wearing those Nike shoes and his total hang time is 3 seconds, that's the total time he's in the air from jump to land. So we need to figure out what's his height here. First, total time of this jump is 3 seconds. That means to go up is 1.5 seconds. To land back on the ground is 1.5 seconds. So the time we're actually going to use in our equation is 1.5 seconds. His max height, we're not sure of. His initial height was 0 if he's starting from rest. Why I? What would his velocity be at his max height at the instant he reaches that top crevice of his jump? That velocity is actually going to be 0 at the max height. Now, depending on how we're going to plug in, this could be a VI, this could be a VF. I'm going to leave that up in the air for you to figure out. But these are the variables we're given for this problem. Can you figure out what his max height is? If his hang time is 3 seconds, use this information to help you. Check out the answers when you're ready, and good luck.